Rudy, are you saving questions till the end? Should I plan to just kind of continue through?
Yes, yes. Before you continue speaking, questions will be at the end, yes.
Great.
Okay, good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems program here at Lehigh University. And to the students, welcome back from spring break. I'm sure you guys are excited about getting back to school. We've got a very interesting talk today, and we've had presentations in the past from this company, from the CEO and the CFO of this company. And obviously, since then, of course, a lot of progress has been made. So the topic for today's presentation by ELYSE DOYLE is leading the energy transition, the challenge, the opportunities, and why your superpowers matter. And all these words are being very carefully chosen by ELYSE, I know, and I think it's really pulls on all the strings that are needed to make this succeed. Let me read the abstract and then introduce her. The energy transition is a momentous challenge requiring the best and brightest minds with diverse skills and backgrounds. This discussion will highlight a first-of-a-kind energy storage system developed by Malta, Inc., using molten salt technology as its energy storage medium. It is long-duration energy storage. You know, this is the holy grail, and it'll enable the decarbonization of the electric sector globally. A fossil-free energy future requires technology like Malta's that provides synchronous and dependable energy when it's needed. The Malta technology can enable coal repurposing and provide cities with district heating opportunities due to natural heat extraction as part of its energy generating process. The Malta team is engineering this first-of-a-kind solution to provide the momentum to enable the transition. Even so, the energy transition is not just about solving technology or engineering challenge. To be successful, we must address the political and regulatory barriers, the need for security, the need for affordable and accessible clean energy, the workforce, and the need to make substantial investments in green infrastructure. I think these points are very important to stress, and I'm really glad that at least that you could spend some time talking about this. A little bit about ELYSE. She joined Malta as a project manager for the Malta product team in February 2021, managing projects and operations. Her projects focus on the design and development of Malta's first-of-a-kind 100-megawatt energy storage system of bulk-scale long-duration technology. She manages an internal multidisciplinary team of engineers as well as external global partners responsible for detailed engineering and major equipment delivery. Before Malta, she spent nearly 6 years as a consultant and project manager for DNV, working with the investor-owned utilities and energy efficiency program administrators. During her career, her focus spanned oversight of large project teams to big data projects, inclusive of data management, data ingest, process and quality control, as well as serving as a customer's primary interface point. She received her master's in economics and her bachelor's in financial economics from the University of Maine. She holds a project management professional certification from the Project Management Institute, and she teaches part-time in Northeastern University. So welcome, ELYSE. And before I start, I just want to remind everybody that she will talk for roughly 60 minutes. And then the first set of questions will be open to the students first. They will have first dibs. either through audio or through the chat box, and then I'll let the others get involved. All right, ELYSE, it's all yours.
Wonderful. Thank you, Rudy, for the introduction. Hello, everyone. I'm ELYSE. I am, as Rudy mentioned, the project manager at Malta. It's a startup company that's developing a long duration energy storage system. And as he mentioned, specifically, I manage the design and development of that first of a kind system that we are building at Malta. I am very excited to speak with you all today. I was honored to be asked. I think it is important to talk about, our current climate challenges, also what they represent in terms of opportunities with renewable energy and energy storage, and end with an explanation on what I mean by superpowers and why they matter. So I will share my screen, and if Rudy, maybe you can let me know when you see it, that would be great.
Yes, we can see it, ELYSE.
Okay, let's get started. So why energy storage? Why renewable energy and electrification? Why are those topics so important? At this point, I think it's no surprise that more and more frequently we are seeing the impacts of climate change and their severity increasing across the globe. We're seeing record droughts, forest fires, floods, warming oceans, melting glaciers more so than we have before. And these are just a few of many examples in the news that truly highlight the urgency of all of us to change the way we're living, and in particular, the way that we are generating and using energy. And I'm gonna highlight my point with a quick video. This was published by NASA in January of this year on reflecting on some of the climate change impacts that the Earth experienced in 2022, and just share a little bit about what NASA's doing to try to improve the situation.
"2022 was an extraordinary year. We traveled to the moon again for the first time in half a century. We made history with the James Webb Space Telescope, seeing deeper into the universe than ever before. And those same folks exploring outward are also the same people looking inward toward Earth. So what did we see this past year? A lot. Scientists around the world determined that greenhouse gas emissions that drive climate change once again set new records. In July, we sent a new instrument called EMIT to the International Space Station. EMIT can identify super emitters of methane, a powerful greenhouse gas coming from pipelines, landfills, and other sources. And it's already recorded super plumes all over the world, including in Turkmenistan, Iran, and New Mexico. Methane, carbon dioxide, and other greenhouse gases trap heat in the climate system and cause rising global surface temperatures. 2022 effectively tied for Earth's 5th warmest year since 1880, and the last 9 consecutive years have been the warmest 9 on record. And all that heat expressed itself differently across the globe this year. Most of the extra heat in the climate system builds up in the ocean. And 2022 set new records for ocean heat in independent NOAA and NASA analyses. This increased ocean heat can fuel intense tropical storms, like we saw in September with Hurricane Ian. Ian rapidly intensified from a tropical storm into a Category 4 in under 24 hours, and became one of the costliest storms to ever hit the US. As the climate system warms, the atmosphere holds more moisture, resulting in more intense heavy downpours. From June through September, Pakistan saw some of the worst flooding in a decade due to prolonged and intense monsoon rains, leaving behind a devastated community. Increasing heat not only leads to more water in the atmosphere and heavier downpours, but it also exacerbates soil moisture loss and drought, which is what we saw in the American West as it experienced ongoing droughts in 2022, leading to vital water reservoirs like Lake Mead and Lake Powell dropping to just 27% of capacity. Drier and warmer conditions means there's more fuel and opportunities for fires. In January, during a long-standing heat wave and drought, the Corrientes province in Argentina saw over 1,000 fires. It devastated important wetlands in Iberia National Park and vital surrounding farmland. But there is hope looking ahead. In addition to monitoring Earth, NASA is powering solutions with free and open data, like OpenET, a tool for farmers and other resource managers to plan and implement irrigation and water use in a warming world. NASA know-how is also helping firefighters and forest managers prevent future fire hazards by better controlling airspace during prescribed burns and emergency response. As we've seen, a warming climate impacts all of us, and it's gonna take all of us to combat it. As we look back at 2022 and years past, we see that each year we better understand the challenges we face and how important it is to meet them.
Great, thank you for letting me share that. I thought that that video did a nice job reflecting on last year with respect to the environment and sort of what we saw across the world. It also sets the stage really nicely for, you know, the sense of urgency of this issue and what I'm about to talk about throughout the rest of the presentation. So when we talk about warming of the Earth, they reference that in the video, NASA. I think at this point, it's pretty widely accepted that most of this is due to greenhouse gas emissions, otherwise known as GSGs. So these two pie charts, they are taking a look at some of the largest GSG emissions, contributors to emissions. The one on the right is global, and the one on the left is just the US. But you'll see that they are pretty similar. So in the US, electricity accounts for 25% of GSGs, but when you add on transportation and industry, that accounts for roughly 70% of greenhouse gas emissions from the US in 2019. And on the right side pie chart, you see energy, so that big red chunk consisting of industry, transportation, and electricity or energy use in buildings, making up around 73%. So it's no surprise that decarbonizing the energy sector should result in significant greenhouse gas reductions. So this means electrification, utilizing renewable energy generating sources such as solar and wind, are vital parts of this effort of reducing greenhouse gas emissions and the rate of, the Earth warming. So how does decarbonization work? Luckily, right now, renewables are one of the cheapest forms of energy, so they are being adopted more widely and are more readily available, which is fantastic. It matters that a technology is not only technologically feasible, but economically feasible as well. That's a really important aspect to make sure that it can be successful in the real world, in the market. But I'm going to show you through this pretty high-level simulation how using only renewable energy sources to generate electricity is not enough to support the energy need. So this red line depicts electricity demand, or what we call load. And it's fairly predictable from day to day. Usually the greatest load peaks are in the evening, like around dinner time. And then they tend to, taper off throughout the night, early morning, you're not really using a lot of electricity, and it's relatively a consistent pattern day to day. So now let's layer in a predictable renewable energy source. A good example of this is hydropower. It's consistent power. However, you'll see that it doesn't generate nearly enough electricity to reach that level of demand. So we need more. So now we'll layer in some solar. You'll notice it shows a similar cyclical predictability to demand. It has, peaks, consistent peaks, right? When the sun is shining high in the sky versus when it's setting, and at night there's virtually none. But you'll notice if you look at this chart is that the peaks in solar generation don't necessarily align with the peaks in demand, right? It's a little bit offset. So when you add more solar generation, all you're doing is adding more energy for those particular parts of the day when the sun is shining, and not necessarily in the evening when the demand is high. So, the one benefit of solar, the biggest benefit, is that it is predictable. Every day the sun comes up, every day the sun goes down. Finally, I will layer in wind. Now, wind can be an enormous source of energy generation. In some days, producing way more energy than we need, higher than the demand. But it is not predictable. There can be entire days when the wind is not blowing. And what happens is that creates these gaps, right? These gaps where we have all of our renewable generating energy sources online, they're working, but some days it's just not enough wind, sun, and hydro to fill the need of electricity on particular days. So right now, utilities that are utilizing renewable energy sources, they fill that gap with their fossil assets, like coal plants. And this is okay, but again, we're trying to retire those fossil assets to help reduce greenhouse gas emissions. So this presents a really unique opportunity for energy storage system to fill that gap instead of fossil fuels. Because what energy storage can do is it allows you to time shift the energy. And what I mean by that is on the days when there is an excess, it's a really windy day, there's a lot of sun, the marginal cost of generating that electricity is very low. So on those days, you would charge your energy storage system. You would utilize that wasted energy to charge up your system and get it ready. And then in the evening, when the demand for energy is high and the supply is low, so the sun is setting, maybe there is no wind that day, then you would use your energy storage system to then generate the electricity needed to fill the gaps. So that's when the marginal cost of generating the electricity is very high. The demand is high and the supply is low. We believe at Malta that long duration energy storage fulfills that need. Not just our system, but any long duration energy storage technology is going to help solve that problem. So I also want to make a point to highlight the importance of government and policies as well in this landscape. So it's not only important that, again, that a technology is technologically viable, it also has to be economically viable. So this past August, some of you may be aware, the United States signed into law something called the Inflation Reduction Act. in that act, it gives significant tax credits and other incentives to energy storage technologies, as well as, to support their project development. And this has skyrocketed investment and interest in energy storage systems this year. It's allowed them, again, to become more economically feasible to implement as part of the grid, which supports a future where you can have fully renewable generating assets that are also allow consistent electricity. If you design a storage technology that has been engineered and has been tested and proven that it works, but it's so expensive and that it's resulting in high electricity costs to users like you and I, chances are it's not going to make it in the real world. It's going to be too expensive. It's not going to make sense. So unless you have, some significant government subsidies or credits. So the point I just want to highlight here again is an energy storage solution also has to be economically feasible so that it can survive in this new market. So let me talk quickly just about Malta, for those of you that are not aware of Malta as a company. So Malta became a company in 2018. I just wanted to show kind of a very high level timeline of our history and where we are today. We spun out of Google X in 2018 after graduating from Google's Moonshot Factory. The Moonshot Factory is a pretty famous, well-known innovation incubation program where new ideas, new innovations are tested very rigorously to see if they more or less make sense fit in new technologies. And famously, this program also celebrates failures as part of their progress. So if something ends up not passing a test and not being successful, that team will celebrate that as a win, as an important outcome, just as important as finding things that can be successful. The brainchild, so to speak, for the idea of the Malta system, how it works, came from a physics professor at Stanford University. His name's Bob Laughlin. And his insight was that you could take a heat pump on the charge side of your system when you want to charge electricity, and a heat engine on the generation side when you're ready to generate electricity. And if you put thermal energy storage in the middle in the form of molten salt on the hot side and a commodity antifreeze fluid on the cold side, what would result could be low cost, long duration energy storage. And that is more or less the foundation of our Malta system and how it works. So since then, since 2018, when we became a company, we have completed substantial work developing our conceptual design for the product, working closely with our equipment suppliers, Alfa Laval and Siemens Energy, named the big two. We also worked really closely with some potential customers in North America and in Europe, primarily Spain, to help define our product requirements. What was really important to these customers? What certain types of reliabilities and guarantees do we want to make sure that our system consists of to align with their needs, right? It was important to get that feedback in our design as well. So with the help of our engineering partner, Proman in Portugal, we will be completing the preliminary design of our first of a kind product by the end of this month, which is really exciting. And then the next step for our team is to further refine the design with respect to our first site, which is going to be in Orlando, Florida. This leads me to another important recent milestone that I highlighted here is that this past year, we signed a commercial term sheet with the Orlando Utilities Commission, OUC, in Florida. And this is important because even though Malta's technology has been tested and de-risked and engineered and has, government support for financing, if a customer doesn't find us attractive, i.e. reliable, cost-effective, makes sense for their investments, then we will never be successful. So it was really important for us to hit this milestone as a company to get a first customer on board for our first product. And it's important to note that these types of milestones are really important for Malta, but for really any startup company in order to continue to receive fundraising, what we call here our Series A, B, C fundraises. We must hit these key milestones because this really proves our progress. It proves that we are, creating value. We're progressing in alignment with our board members and with our investors. So signing this commercial term sheet with a potential with our first customer and completing the engineering design of the product at a certain level of maturity were two really important milestones, recent milestones for Malta as a company. Here is just a quick snapshot of some of our world-class partners that I referenced on the prior slide. Some of these partners are helping us with equipment development. So I mentioned Siemens Energy, who will be providing our turbo machinery, and Alfa Laval, who will be providing our heat exchangers. And those are the two really core components of the Malta system, and I'll describe that in a little more detail in a moment. But some of these companies, like Proman, for example, are a big financial investor as well as our engineering partner. So they're helping us complete this first of a kind preliminary design of the product in and of itself. And then we have other investors here. Obviously, we would not be able to be a company and to progress without them. So I just wanted to quickly highlight some of those important names that really make up the entirety of Malta. So how does Malta system work? I hope some of you have heard of thermal storage. So a certain, not a battery, a different way of storing energy, and Malta is more or less based on that premise. So far, I've discussed the need for more renewables to reduce greenhouse gas emissions and the need to provide affordable and reliable electricity to customers when they need it. So again, filling that gap I showed. And that's the result, of just purely having renewable generation. So at Malta, we are developing a grid scale long duration energy storage system. So what that means is a lot of electricity over very long durations. So it's not a system that would be used by an individual or a corporation or an industry. This is really for utility companies to use. Those are our customers. We are designing the product to generate up to 100 megawatts of electricity and to provide electricity for 8 hours up to 8 days. So that just gives you a scale of the level of energy that our system is going to charge and generate. It's also important to highlight that the key components of the Malta system, so I mentioned the turbo machinery provided by Siemens being one of them, and the heat exchangers by Alfa Laval being the other one. These are more or less technically mature equipment that are already used in power plants around the world. And this rather simplified graphic, I think, does a nice job explaining how the Malta system works. So number one, first step of the process is collecting energy, and that can come from any generation source. So that can come from, obviously, renewables like solar and wind, but Malta can also take a charge from fossil generating energy to align with many of utilities' existing assets as we sort of make that transition into having full renewable generation in the future. Once electricity is gathered, is pulled from the grid, again, during a time when the marginal cost is low and there's excess, this drives a heat pump. This energy that's pulled in drives a heat pump. And that heat pump converts electrical energy into thermal energy by creating a temperature difference. So very similar to how a heat pump would work in your home if you have one. So the heat from the thermal difference is stored as molten salt, as I mentioned earlier. And the cold is stored in a chilled liquid. So these are stored in essentially these huge containers. And it's held there, right, until energy is needed. And so when it's needed, so at the end of the day, during the nighttime, the temperature difference is converted back to electrical energy. And this is done using a heat engine. And finally, electricity is sent back to the grid using a similar compressor and turbine that took the electricity during charge. And a bonus of our generation, Malta's specific, the way that we generate electricity, is that a natural byproduct of that process is clean heat. So our discharge process, again, our generation of electricity process releases heat, steam. And this can be used for district heating or other industrial uses, which has become really important and a really valuable addition for a lot of the customers that we've talked to. They found that really attractive as, you know, a unique add that our system offers specifically. So I'm gonna share one more video. Again, I just think it does a really nice job describing a bit about, you know, Malta, our system. This is our CEO, as you mentioned earlier, Rudy. This is Ramya Swaminathan. And I'm gonna start the video a bit later when we kind of jump into talking about the Malta technology. So just give me one moment. And I hope that all of you recognize the voice of the narrator. We'll talk after. Among Malta's goals is to solve the greatest threat to decarbonization, the sun setting. Solar power is the fastest growing electricity source. It provides us with low-cost, emissions-free energy, but only when the sun is shining. Of course, we can't stop the Earth from rotating, but with Malta's innovative new technology, we can do the next best thing. Malta has pioneered a new flexible, cost-effective, utility-scale energy storage solution that can enable 24/7 use of clean power from variable renewable sources like solar or wind, even when the sun isn't shining or the wind isn't blowing. In fact, a Malta pumped heat energy storage plant can store 100 megawatts of energy from 8 hours to 8 days or more. Here's how. Malta's innovative pumped heat energy storage plant takes electricity, either clean energy directly from renewables or by pulling from the grid, and converts it to thermal energy. This thermal energy is stored in two mediums, as heat in molten salt and as cold, which is stored in a chilled liquid. In these forms, this energy can be efficiently stored for long durations. When energy is later needed, the system operates as a heat engine, combining the stored heat and cold together to regenerate electricity. This electricity is dispatched onto the grid, effectively time-shifting the energy from when it's generated to when it's needed most. But why salt? Molten salt is the most mature technology used in thermal storage, with applications in concentrated solar plants and even nuclear power plants. The nitrate salts used by Malta hold heat well and are safe, making them a sensible thermal energy storage medium. A Malta pumped heat energy storage plant repurposes conventional components with a long and proven record in the field. Made from some of the safest and most abundant materials, steel, cement, salt, and air, the components used in Malta's system bypass most critical sourcing challenges and dramatic commodity price fluctuations. In addition, every component and material used in Malta's energy storage plant is fully recyclable and can be reclaimed or reused after its operational lifespan. We are 100% circular.
Because the Malta system is built on proven technologies and equipment, we leverage a robust community of existing technical skills, manufacturing processes, and supply chains. Whereas other technologies have different scientific or supply chain challenges that slow down development, Malta can rapidly deploy its utility-scale, synchronous, long-duration energy storage solutions without delay. And that's how Malta can bring about a brighter, cleaner energy future, even after the sun sets. You can learn more about Malta and our pumped heat energy storage breakthrough on our website, maltainc.com.
So did you recognize the narration voice? It's me. I did that video with Ramya, again, our CEO. So again, just wanted to share, I thought it did a nice job describing a bit about how the system works and some of the unique values of Malta system specifically. So this is a schematic rendering of what our system looks like following our conceptual design of the system. So this isn't at a site specifically. It can be rearranged, the tanks and other parts of the system outside of that, core centerpiece to be fit in around different sites, which is nice. So this is just sort of a product level schematic. And as you can see, it looks pretty similar to an existing or traditional power plant, like a coal plant. If you were to drive by, you wouldn't really perhaps know that it was a storage plant. And I mentioned some of these bullets earlier, but the core value that I want to emphasize with this slide and how the Malta system is unique to other technologies is that, we're trying to avoid creating a brand new technology with a lot of risk that's going to take a long time to come to market. So the fact that we are able to use existing technologies, so turbo machinery and heat exchangers that are already used in power plants, and nitrate salt and a methanol coolant antifreeze that are pretty abundant, cheap commodities, is that this makes it a lot easier for our system to come to market. And we're also able to utilize resources from utilities' existing assets. So utilities, we've been discussing with a lot of utilities about repurposing coal plants into Malta systems because a lot of the equipment and the resources are also applicable to a Malta system. And I also want to highlight, I mentioned this briefly earlier, is the generation of this green heat that through our electricity generating process, heat naturally is exhausted. And if we are able to harness that heat, which we have the ability to do so for customers to use, again, as a district heating option, for example, which has traditionally been really hard to decarbonize, this would make our system over 90% efficient. And so to put that into some perspective, the average efficiency of fossil-fueled power plants in the US is around 36%, which means that 64% of the energy that's used to produce electricity in those power plants is wasted in the form of heat just discharged into the atmosphere. So the ability to harness and use the excess heat generated from our system means that almost all of the energy used to produce electricity is being used and not lost. All right, I'm going to switch gears a little bit now. In the title of my presentation, I do talk about superpowers, right? Why do your superpowers matter in this environment, in this new landscape with renewable energy and energy storage, really catapulting forward in the market? And so by superpowers, I don't just mean the degree that you received in college and what you studied. although those are valuable. But I also mean the many skills and attributes that you have inherently that make you happy, that make you feel connected to others, that help you be successful ultimately in life and in your career. Many of these other skills are often referred to as soft skills, such as emotional intelligence, communication, leadership, et cetera, et cetera. And not only are those skills no less important than the technical skills that you learn in school, but they become more and more important as you progress throughout your life and career. A CEO isn't a CEO because they can make great spreadsheets. A CEO is ultimately a CEO because they are excellent communicators and fantastic storytellers. They're persuasive. They are natural leaders who motivate others, right? So with the latest government incentives and the latest policies to launch energy storage forward, many different storage technologies are coming to market, and they're all needed. It is a wide bench, so to speak, because they fulfill different needs. They have different values. For example, a battery technology is really important and to be used for residential and commercial use on more of a smaller scale. At the same time, larger systems such as Malta are also really important to support grid reliability and resiliency so that we can put all of our fossil assets offline safely and reliably. So just as with these differing technologies, your unique skills, experience, education, and soft skills, your superpowers, they are also needed in all aspects of this growing industry. So yes, scientists and engineers are very important people that we need to help solve this problem, but truly all superpowers are needed. And I will share just a quick example using Malta as a company. So, as a company, you'll see that we need more skills than just engineers on our team. We need experience from a broad range of skill sets to make sure that we can be successful. So yes, that does include technical skills to design and develop the product, but it involves so much more. For example, the product development team needs an organized and forward-thinking project manager. That's me, to help keep the design on track so that we also meet our schedule and our cost targets. Our company, although I think it's fair to say this is true for all companies, also needs people with experience in financing commercial utility projects. We need legal experience for the many contracts that we're using with customers and any other legal documents used to help support our financing. We need people with marketing and analytics experience to help find the most suitable customers and understand some of our competitors. We need people who can do environmental permitting for local environmental studies on sites to make sure that we're not disturbing any habitats, right? If we were to build a system on that site. So the list goes on and on. This is a quick snapshot of our team and the diversity of our team. So even with just 25 employees, we have 5 very different segments of our company. So that's engineering, legal, finance, program management, and commercial, just right now. And we are growing and we will be getting more. And even within some of these segments, we already have people with really specialized skills that, help contribute to the team and ultimately, our entire success. In addition to having diverse skills and experience, our team is also very globally diverse. We have many team members across North America, including Boston, where Malta was first instituted. But we also have people in New York, Atlanta, Florida, Canada, as well as team members in Europe. So Spain, Italy, Germany, we're very diverse. And we think that that's important. You know, we celebrate that because that is what's going to help us solve these really complex problems, is having unique perspectives and diverse teams with diverse experiences and backgrounds. So to summarize, the environmental challenges that we face are here. They are real and they are substantial. No one, I think, is denying that. Long duration energy storage can help reduce greenhouse gas emissions while also ensuring consistent, reliable electricity when it's paired with renewable energy. The Malta system is one of the many storage solutions to help close the gap with renewable energy generation, while also allowing utility companies to use many of their existing fossil plant assets as they begin to retire those assets. And the US government and other governments around the world are catching on to the importance of energy storage, and their policies will catapult the needed investments for these technologies so that they are not only technologically feasible, but also economically feasible to be successful in the market. And last but not least, everyone's superpowers are needed to help solve this climate problem. So whether you work for an energy storage company like me, or you work for an environmental agency to perform, environmental studies, or the government to help push some of these important policies forward, everyone's strengths are needed. So I'm going to stop sharing for a moment, and I just want to, in my final time here with my presentation, share a personal story with you to kind of highlight the importance of your superpowers. So a little bit about me. Rudy mentioned this in the beginning of the call, but my background is in economics. That's what I studied, which is considered a social science. I received my master's in economics in 2015, and then I worked as a data analyst for utility companies shortly thereafter, and I obtained my project management professional PMP certification in May of 2020. So I have been a practicing project manager for about 5 years in total in the energy industry. And when I interviewed with Malta 2 years ago, I was told that I would be working on the product development team, which was that time, i.e. the engineering team. And this is a team of brilliant, highly skilled engineers with PhDs or 20 plus years of experience working on power plants around the world. So as you can imagine, I was slightly terrified, having never worked with such a technical team before of that caliber. And I felt like my skill sets, like my strengths, communication, organization, analytical thinking, I didn't think they were good enough to be on that team. So I was really nervous. And now fast forward 2 years later, I'm so grateful that I did not listen to that scared voice in my head. And that I took the position here as project manager for the technical team, because I have learned a tremendous amount from that technical team that I work with. But what surprised me was that my lack of engineering experience actually became my superpower on the team. So I was able to bring a unique perspective that was different than all the other team members. And I had the freedom to ask, maybe the silly questions that actually made the engineers kind of stop and think, and in some cases reconsider a decision that was being made. I brought organization to the team. I brought standard processes to the team that were desperately needed. And now they rely on me just as much as I rely on them to help us meet our deadlines and, complete our design on time and on budget, which is the goal for all of us. So I hope that gives a nice flavor to what I mean by superpowers, and how, you know, your soft skills in many cases are just as much, if not more important, as you progress in your career, and particularly in this new and exciting and important industry in renewables and energy storage. So thank you very much for having me today and giving the presentation. That's all I have. So I'm about 10 minutes early, but I would rather be early to allow more time for questions. So with that, Rudy, I will hand the mic back to you to facilitate questions.
Well, thank you very much, ELYSE. And I just want to segue into your last few words. You know, you mentioned soft skills, and really the program emphasizes not only knowledge of hard skills, knowing about how generation works, distribution works, but also how do you communicate this to people who utilize this energy, may not be as well versed as you.
Fantastic.
You support in so many different ways, you know, as to what are some of the superpowers that are needed. You know, it's not just engineers and technical folks who are involved in energy, but a whole bunch of others like you, economics background, finance, and so on. All right, so what I thank you again, ELYSE, for the wonderful talk. And so as I had mentioned before, I want to open the floor now to the students. If you want to ask your question orally, please unmute yourself, introduce yourself, and go ahead with your question. All right, so students, you're on. Unmute yourself, introduce yourself.
Hi, I have a question. My name is Alexander Gardner. I'm a student here at the ESE program. Thank you for your talk. I think that was really interesting. Energy storage is super cool. My question is kind of on the economical side of things. So am I getting it right that you guys will purchase power from like a utility scale solar generation site, store it yourself, and then the idea is to sell it back to the grid? And I was wondering, do you get that much more of like a revenue from selling it back to the grid at those peak demand times? And is that, you know, difference between selling it at the peak demand time versus the normal solar generation time, is that what I guess funds all of the operations, that along with, I know, the incentives you mentioned?
That's a great question, Alex. And I think we're trying to figure out what our first project business plan is going to look like. I think there are a lot of options, and because it's not sort of it's almost like a pilot right now still, we have to take that into consideration and not really be going out of the gate looking for revenue in the first project that we do, but really wanting to partner, like truly partner with a utility who would be, you know, really putting up the front money and investment in our system, working with them to work out the kinks, make sure that the system makes sense with all of their other assets. But yes, in the long run, we would be selling our product as an asset to utilities. It would be getting a revenue for if and when they used our electricity. So when the marginal cost is high, that is when we are truly really valuable to the utility. So you understood that, the economics of that correctly. When there is not as much supply, especially renewable supply, that is when utilizing our system is the most valuable, and profiting for Malta.
So sorry, does it is it Malta that's like, I guess, officially selling it or would be selling it back to the grid, or is it still like utility that owns the electricity and is taking it back?
It would, in what we are trying to set up in the long run, it would be the utility that owns our system, and it's just part of how they, generate utility back to the grid.
Okay, cool. Thank you.
Mm-hmm.
Question for ELYSE. Unmute yourself and introduce yourself.
Hi, ELYSE. My name is Garrett Moyer. I'm a current ESE student, and I also work full-time for an electric utility. I was wondering, as far as how quickly like your system can transition from storage to generation? Is it more of like a scheduled thing where you're saying at peak demand hours, maybe in the evening from 4 to 5, 4 to 8 or whatever you're generating, and then you're buying overnight? Or is it something that's more dynamic and can be switched based on utility operators?
Hi, Garrett. Thanks for the question. That is a really great question. So right now, the way that we're designing our first product is that it would take about 8 hours to switch. But there is absolutely the ability to change that. Like, we have the ability to do in future products that we design, sort of like a rapid charge, but also like a slow trickle charge. And we could do a rapid generation if it was needed. So those options are definitely on the table. But right now it takes about 8 hours to make that switch. So it would be more in a world where you would, charge it during the day and hold it. And then in the evening and at night is when you would, discharge.
Gotcha. Thank you. Appreciate it.
Yeah, thank you.
All right. Questions for ELYSE?
Rudy, I believe Jose, one of our ESE students, had a question in the chat.
Who's that?
Jose Suarez.
Hi, Rudy.
Yeah, go ahead.
Hi.
Go
Jose,
ahead.
do you want to ask your question
Yes,
Yeah,
go ahead.
sure.
now? Great.
Thank you, Elise. My question was more about the power sources for thermal storage. Sorry. Are renewables, specifically solar and wind, being looked at exclusively to generate that power, or are other power sources being considered as well?
Yeah, great question, Jose. So right now, all generation sources are being considered, so that our system can already get implemented as soon as possible, while utilities are, still using their existing fossil assets. I think that's going to help a lot with also better understanding our system, since it is very similar to a traditional fossil generating system. But our real value, though, is to ultimately replace those other forms of traditional energy generation, and be in a world where it's purely renewable energy generation. So the big ones, are solar, wind, and hydro right now.
Thank you.
Thank you.
So ELYSE, I have a question on the efficiencies. So when you take the thermal energy storage and convert it to electricity, you're obviously you're limited by Carnot efficiencies and so on. So you mentioned you get 36 or 37% conversion efficiency. So you utilize the remaining heat energy for district heating and so on to be able to really claim the 90% total overall efficiency. Do I have that correct?
That's correct.
Okay.
And
All
right now, we are designing that as a feature offering. So a system that has a customer that is going to also utilize that will have like an additional component to allow it to convert to different forms of heat, whatever is more useful to the customer. It would be an added feature to the product.
Okay, questions for ELYSE, students? All right, so I'm going to now ask the general audience to ask questions. I know there are some in the chat box, so if you wish to articulate your question, go ahead, unmute yourself and ask a question, please. So if I may read a question from Carlos Romero, Dr. Romero, what is the COP of the heat pump, the thermal efficiency of the heat engine, or the overall DC-DC round trip efficiency for the system?
Those are great questions. They are good examples of our product requirements. So we have a certain set of efficiency requirements that we are currently monitoring as we design the product and make trade-offs on cost, and making sure we also can hit some of those key requirements. I don't know the efficiencies of the specific equipment, so the turbo machinery. I think that's still being worked out in terms of sort of what it can guarantee. But I know that our product as a whole, which is the combination of all of our component efficiencies and how we run, we're looking at overall system efficiency instead of RTE. And that's primarily because our customers, the utility companies, they're mostly interested in that number. And right now, I have to think back of our last review. Right now, off the top of my head, I think that's close to like 49–50%. And again, that's overall system efficiency, which from what I understand is different than round trip efficiency. Hopefully that makes sense.
Okay.
I'm happy to follow up too.
Carlos, if you want to follow up with any questions that you have, please go ahead.
Sure, these are good answers. Thank you very much. I will get back to you if I need more information. Thank you.
Great, you're welcome.
Can I pose my question at this point?
Right. Question from James?
Yes. If you look at the nighttime view of the country, you find that most of the electric energy is used east of the Mississippi. That's where the population of mega metropolitan areas is its highest. So my question is, pre-pandemic, New York City had a peak demand in excess of 15,000 megawatts. I recently certified a 6 megawatt photovoltaic solar field that covered 45 acres. There's a request for installing an 80 megawatt solar field that's going to require clearing 550 acres of forest. Now, that would approximate for New York City 112,500 acres. So the question is three-part. Where would this energy system put its capture its solar field? What would be the energy source, and what would be its footprint for your conversion from this solar energy input to an output of electric power to a grid?
Thank you, James.
Intense.
No, so if I understand your question, you have a couple of questions in here. So footprint of the system, sort of where it would be located in that example. I think one of the values of what we're designing is that it can be, depending on the site. Obviously, we're attracted more to like brownfield sites right now. We don't want to have customers like clear cut land. I mean, that's an important consideration in our product. Our footprint is around, let me get back to you. I don't want to take a wild guess. Because it's changing all the time. So let me get back to you on the actual footprint, current footprint of the system. But
just let me know in megawatts per acre.
Okay. I can send that to you.
Okay. So ELYSE, I have a related question. You use molten salt, and I've assumed that these are higher temperatures than you would with say using steam or something like that. So when you talk about repurposing existing coal plant, the secondary systems, as it were, do you have to think of the materials that are being used, or do they need to be enhanced, like stronger piping, turbine blades need to be different, or?
Yeah, great question. So absolutely. I think it's on a case-by-case basis. I know that we are, the reason why we are partnering with Siemens and Alfa Laval specifically is that we want to make sure we're designing the best equipment, or it's more like tweaking existing equipment, but it is still specialized equipment for Malta system. So it is the turbo machinery that's being used in a Malta system is slightly different than the turbo machinery that's used in like a combined cycle power plant, for example. So we wouldn't be able to substitute those pieces of core equipment. I think what is becoming more realistic is the facilities, sharing facilities, using current operators, electrical rooms, for example, the current like connections to the grid system. And yeah, I think again, it's on a case by case basis, but absolutely, like we have our set of design basis requirements that like our piping, because it's such high heat, it has to be at a certain grade, it has to be at a certain diameter. I mean, those things are really important. So for our system to offer, you know, what it says it's going to offer. And so that would be looked at very closely. Yes.
Okay, so you'll have to go through a process of commissioning a plant, which is a storage based. Okay.
Yes, exactly.
Good. Questions? Let me see any more questions on the chat box. Let's see. I don't know if Joe Andrusani's around. You've got a few questions there. Joe, you want to articulate them? You read it out. How does,
Yeah, yes, Rudy. Can you hear me? Yeah,
Yes.
I had two questions. One had to do with you mentioned 100 megawatts as kind of a first project. How does how would this scale up as you go to larger tanks? Your thermal losses would increase. So I'm just wondering, from a capital project cost, you know, how does this scale? And, you know, or is this kind of your sweet spot? That's one question.
Thank you, Joe. So you are right. When we think about scaling up for Malta, it would be adding more salt and more coolant. So it would be increasing the size of our tanks and our storage capacity. And you're right that that would result in, you know, more thermal loss. So I think there will never be an instance where, you know, we make a substitution without having like a full trade study and analyzing the trade-offs of that system. I know that we landed on 100 megawatts because from an efficiency perspective and cost perspective and customer preference perspective, that was kind of where everything started to fall together. We are offering the ability to change the, you know, based on our tank sizes, the amount of storage that we would offer, but those would need to be fully engineered, like additional applications or, you know, other products that we would offer in the future.
I see. Thank you. One thought on that would be you could always go to a parallel approach, just put in more parallel units to keep, you know, the thermal factors the same, but then you get into footprint, as the other gentleman was.
There's always you pull one end and the other end, right, comes out is what we're realizing. You're right. Yeah. But no, I really appreciate the note. I took note of it.
One last question. If I was a utility, you know, and I was considering various options, how can I get 100 megawatts, you know, of basically extra power during the evening? I have your option, Malta, and what does that cost me? Versus, I've been hearing more about these small modular nuclear reactors. How much would it cost them to just increase their base load so that they move out of this regime of being short in the evening?
That's a great question. I don't know specifically what the cost trade-off would be of choosing Malta versus the modular nuclear power. I think the added values of, you know, utilizing a fossil facility, helping a utility repurpose that is an added value that Malta can provide. And I also think, you know, offering that additional district heat as a natural, byproduct of our generation system is also something that a lot of cities have reached out to us that they've really been interested in that. So I think those are the two kind of unique value points I would point to for Malta. But again, every utility's sort of setup and their resources and their challenges are unique. So yeah, I think there's room for all technologies. I truly believe that.
Yes, thank you. Yeah, the district heat would seem very appropriate to cities or where you have close by, where transmission of heat would make sense.
Yes, exactly. Thank you.
Hi, ELYSE. Thank you so much for your presentation. My name's Ava Hudson. I'm a current ESE student. So you mentioned that you guys were attracted, or that Malta was attracted to brownfield sites. So I've kind of two questions. I was wondering if that is due to the tax adder that's available, because a brownfield site would qualify an energy community, as well as if there are current efforts at Malta to identify additional energy communities under the new IRA, just because that's the focus of my capstone project for this semester. So I was just curious if there were similar efforts and if there's other reasons you're attracted to brownfield sites.
Yeah, thank you. So we have been attracted to brownfield sites at our onset. I think it makes the most sense in terms of like what we believe in and helping the environment and not having a large impact on changes to the environment. So even before the Inflation Reduction Act, that was something that we were prioritizing, if we could choose. But certainly you're right. I mean, the Inflation Reduction Act has really honed in on like the importance of that for us, so that we can qualify and get those additional adders. So I think that those specific terms are being like looked at very closely. We've got like our policy liaison and our commercial team to make sure, like, do we need to tweak any of our requirements? I mean, that's definitely something that is worth us looking into and has influenced or strengthened our decision to go towards brownfield sites.
Thank you.
Any questions for ELYSE? So ELYSE, question on waste heat. Malta captures the waste heat and uses it for district heating, claims it as green heat, as you should. But in the past, capturing waste heat, especially from steel making and so on, has been very difficult. So how is it any easier in your case?
That's a great question. I don't know. I'm not sure how it's been attempted to be captured in the past. I know that it is something where we're going to have to re-engineer different options based on the form of heat that particular customer would like. But I can definitely, follow up and get more, answers from our technical team, because I think that's a great question. I'm just not entirely sure.
Well, heat is supposedly a very nefarious form of energy. You can check in, but you can't check out. So I mean, it kind of fights against Mother Nature. It may be difficult to extract the waste heat in a very efficient manner. All right, questions for ELYSE? I think the fact that you're utilizing well-known technologies, repurposing, existing plants are all very positive issues as we go into the energy transition, because, making best use of resources.
Exactly. Yeah. And that's been a big selling point for our customers, obviously, for utility companies. They find that really attractive as they are trying to figure out what to do with these retired assets. How do they minimize their losses as much as possible? And it is something that, we're still figuring it out together. Like right now, we're in the midst of that. So it is exciting.
All right. Have I missed any questions from the chat box, or you're still too shy to unmute yourself and ask a question? Any questions from the audience? Okay. If there are no other questions, going once, going twice. All right, Elise, thank you very much for your presentation. This was very well done. Thank you again. Best of luck. The next thing that we'd hear from Malta, would it be a Southern company or a Duke Energy commissioning a thermal energy storage plant in their service territory? Is that something we should expect?
Well, yeah, I think the most exciting news and what we're going after right now is setting up our first project with the Orlando Utilities Commission. So a large group of engineers last week were in Orlando at the site and really exploring like how can we move certain things around, and it was just really fantastic to see it in person and instead of talking about it in the abstract. So yeah, look for a lot of great press releases on that progress for sure.
Good. All right, again, last call. Any questions? We still got some time, but don't want to keep you guys here if you're done. Elise, thank you very much, and look forward to hearing more from what you guys are doing. And audience, we will have next week a presentation on energy forecasting. So we'll hear a little bit about artificial intelligence and all the cool things that are being done in that field. That'll be next week, same time. The speaker will be from SAS. Thank you all.
Thank you everyone for having me. Thank you, Rudy. I truly appreciate it. Take care.
Thank you very much.
Thank you, Elise.